Hi, Craig. Good morning. First of all, welcome to our INDUS podcast. And we are really honored to have you in this podcast series. So, happy to have you here.
Delighted to be here. Thanks for having me.
Okay. So, Craig, let's start with briefly about your personal journey in this whole scientific field. As we all know, you as a leading scientist in the field of solar and heliospheric physics. But before all that, I would like to ask you that what sparked the curiosity of science when you were a kid or in your school days?
Well, I've always been interested in physics. I loved getting to the bottom of why things are the way they are. And I remember as a child doing things like estimating distances in my head, or trying to really understand things like acceleration. Uh, the Everybody has a story for how they got into their field. And for me, the story with solar physics is I was a Boy Scout. As a young boy, I camped out a lot. And I remember uh, one morning waking up at the dawn on a camping trip and looking at the sunrise and seeing spots on the sun. This would have been right about 1980, so it would have been a solar maximum period. There were naked eye sunspots visible then. And I remember being intrigued by them and asking my dad about them and so forth. But of course, that kind of story is total BS because there were lots of things that were
Yeah,
interesting
true.
I could have ended up doing. Uh, the turning point really was in graduate school. I knew in college that I wanted to do physics. I went in not knowing what I wanted to do, uh, and decided I would just watch and see what courses I chose each year. I gave myself permission to set a schedule of courses that I wanted, and I found that they were all math and physics, with a few electives sprinkled in. So I was a physics major because of that. Uh, and graduate school is very similar. I went to a graduate school that had several subjects I was interested in. Solar physics was one of them, but it was one of three major topics that I thought were candidates. The others were solid state optics and elementary particle physics. So I went to Stanford. They had all three. Uh, and I met up with some solar physicists who had just come back from White Sands Missile Range. They were drinking beer on a Friday afternoon, as that group did, and invited me into the lab to come see their X-ray telescope. They were very enthusiastic. Uh, and I decided to do a quarter with them and never looked back. Uh, the lesson from that is there are lots of interesting problems in the world, but interesting and affable and good people are rarer. If you find a good community, that is much more of a rare thing than an interesting problem to solve. So I ended up coming to solar physics largely because of the community that it spawned.
Oh, yeah, yeah. True, true. Indeed, it's a fantastic community. And your journey from Reed College to doing PhD from Stanford, then being the director of the Solar Heliospheric Division in the SORI, to being the PI of the Punch. So it's beyond inspiring for us. So the thing is that leading a NASA mission from proposal to the launch is no small feat. So what was the initial inspiration, the early stage, the beginning of this Punch mission that you started?
So there, as with a career, there are many starting points. I'll start out by emphasizing being a PI is public service, right? If you do it right, it's not something you do to aggrandize yourself or to for personal gain. It's something you do ideally because you really want the science, and that's what motivated us with Punch. Uh, the deepest start to Punch was in 2011. Other people, the stereo team, had built the first imager,
Really?
the Secchi suite on board stereo, and I had a grant to do some analysis of those images and look at CME models and compare them. Tim Howard and I were working on that. And we got the model working well enough that it predicted the shapes of CMEs after they left the sun. The idea was we're going to look at the CMEs in the heliospheric imager and then compare it to the models. Uh, when he showed me the data, they were horrible. They were running difference movies. The signal to noise ratio was maybe unity, if that. Uh, and we couldn't get out the information we wanted about the structure of the CME. So Tim and I worked for about 8 weeks on trying to background subtract the stereo data. We cracked that and produced images of the solar wind with the star field essentially removed. Uh, and that was exciting, right? Being able to exploit this beautiful mission that had been built. But then all of a sudden, there were a lot of papers to write because we were seeing things nobody had ever seen before. Uh, and having learned then from what went right and what could have been improved with SECI for the imaging characteristics, this was back in 2011. The two of us started working on concepts to prove out heliospheric imaging on a quantitative basis. So we proposed several missions, CubeSats, a space station instrument. We ended up building a ground-based instrument, all to sort of prove this concept would work. And that culminated in 2015 in a science definition meeting that we held here at Southwest, where we decided what science is needed at this point that imaging will address. And once we cataloged it, the structure of the Punch mission sort of became clear. So Punch has been in the works as a mission, a particular concept, since September of 2015.
So indeed, it was very interesting to know how the idea of Punch get inspired through the earlier spacecrafts as well, and through the meetings and the conferences. They are really a great platform to kind of seed these ideas. So the way I see Punch is it is a mission to see the solar wind. I may be wrong. So can you walk us through the vision that you had to bring the broader community and NASA into this?
Certainly. Right now, we're at a very interesting time in heliophysics. Solar physics, the study of the sun as a star off in the distance, uh, and heliospheric physics, the study of the solar wind, are in the process of unifying. Those two fields are merging into heliophysics. Uh, Traditionally, solar physics has been done with telescopes and spectrometers and things, remote sensing what's happening on the surface of the star, or in some cases under it, right? Helioseismic imaging. Uh, Solar wind physics has been done largely by sampling the solar wind ever since Marcia Neugebauer found it in the Mariner data back in the 1960s. Uh, and so the in situ sampling is very good, and it tells you everything you could possibly want to know about the solar wind at a particular place. Uh,
Yes.
Whereas imaging tells you more of the large scale picture, but doesn't tell you everything about the microphysics of what's going on. And those two ways of looking at the world look very different, and they've spawned completely separate communities that, in some cases, can't even really talk to each other. They often don't share the same vocabulary.
Yes.
And so, as solar physics has developed, it's become more and more apparent that we need to understand these outer reaches of the corona in order to better understand the solar wind. Uh, so we have two missions that are sort of making those domains intersect. Parker Solar Probe is bringing in situ sampling inward toward the sun so that we can diagnose exactly what's happening in the corona. Uh, Meanwhile, Punch is sort of the counterpart to that. We're bringing imaging physics outward so that we can see the large and cross-scale images of what's happening in the solar wind. Solar wind is a really interesting system, right? Because uh, the particles are so diffuse, they're so rare in the space that they never collide, right? So, but it's not a stream of particles. It is a fluid. The solar wind is a fluid because the particles exchange momentum via the electric and magnetic fields. Uh, but it's very difficult to discern that fluid character from direct sampling things that hit your spacecraft.
Yeah,
So being able to reveal the turbulence and the motions and the streams is something that I'm really looking forward to over the next few months.
yeah, yeah, true. So the novel thing about the punch is its wild field imaging to study the outer corona and solar wind, and it operates as a constellation of small satellites, very modern and modular approach. So how this design choice came in your mind or in your team, and what advantages does it have?
Like many novel choices, it was something we were forced to make. We realized we had to have a very broad imager.
Yeah,
And the first concept was to go out to L1 or something in deep space and have a single suite of instruments. Uh, but the telemetry costs were very high. Getting all the data back to Earth from that far away and building everything for exposure to deep space was cost prohibitive in the program. So that led us to move to low Earth orbit where we could get the data back more effectively. But then the problem with that is there's a giant planet in the way. So we had to spread out the instrument so that it was as large as the planet.
yeah,
The only way to do that was to put it on four separate modular spacecraft. That led to lots of really interesting challenges in the development. In many ways, the most novel part of this mission is not the instruments themselves. They're pretty cool, but it's the ground processing and the methods we had to develop to merge these data and then to background subtract them to extremely high precision.
yeah, yeah, true, true. So I have talked to some of the members who are working on this punch mission. Ritesh is one of them. I heard that he got the idea while he was watching Avatar 2 in the 3D IMAX. So that's very fascinating that how small problems can be kind of taken care through other interdisciplinary things. So my next question is that what do you think how important is to build an interdisciplinary team? And what are the things that you look while you are building the team? And what are the things that kind of ensure the success of the full mission through that?
Breadth and diversity of approach across a team like this are essential, absolutely essential. Uh, Everybody on the team is human. And so when you assemble a mission, you have to assemble something that's greater than any one of the people in it, even greater than yourself, right? I could not execute punch on my own. And so the trick is to find a team that covers all the different skill sets that are needed. And no one person can do that. The only way to achieve it is to bring people from different backgrounds, sometimes different cultures, so that they can get multiple takes on a problem. Uh, I do believe that that is an essential part of making a team effective, is trying to get a breadth of approaches. Uh, we have scientists who are deeply interested in coding who would not be good at public outreach. We have public outreach people who would not be good at operating a spacecraft, right? So making everyone, making or bringing people in to do the things that they're good at uh, produces a team that overall functions more strongly than any one person could.
Yeah, definitely, definitely. So true. So, as we just discussed, so Punch has already seen its first light. Would you like to comment on that? How exciting was that? And what kind of data is you're most looking up to? Maybe any specific phenomena that would you would like to study using those data, something like that?
Sure. So, just minutes before we started this interview, we opened the doors on the narrow field imager, NIFI, and on one of the wide field imagers, WIFI. Very exciting moment. The doors are heavily engineered because, of course, millions of dollars of investment goes into, well, it's dependent on the door opening properly. And there are lots of interesting engineering challenges to that. But they went smoothly, and in about an hour after this interview, we're expecting to get our first starfield images from both of those spacecraft. That's a very exciting time.
Yeah,
Uh,
true.
the what I'm looking forward to over the next few months as we start taking regular data is, well, there are lots of science objectives, and you can see them on the website. There are specific questions that we formulated, and overall objectives for the science that boil down to understanding the solar wind and understanding space weather. Uh, what I am most excited about is being able to see the corona and wind themselves as a single system. Uh, there are things that we feel viscerally as humans that may or may not fit into our way of thinking about, I'd like a particular science result. These are things like the viewpoint, the perspective on Earth that was captured by Voyager. You may remember when Voyager got pretty far out, somewhere out around Uranus's orbit. They looked backward and did a grand tour of the solar system. They took a picture of everything, including a little blue dot, right? That was
Yeah,
us. It
yeah,
was uh, a group portrait of all of humanity. Uh, and so those moments of changing perspective, I think, are a big part of why we do this enterprise of reaching out into the cosmos. So for Punch, that moment will be seeing this material, this environment that's filling our solar system, that bathes our planet, that's invisible to us every day. And being able to actually see that environment for the first time is something I'm very much looking forward to.
yes, yes. So seeing the kind of origin of solar wind in a fluid manner, that I think it's very interesting. And I'm also looking up to the data, so how it looks. And coming to different spacecrafts that are already there, like Parker Solar Probe or Orbiter. So from the user's perspective, so people will be trying to complement that particular region through PSPs or Orbiter as well as this. So in this scenario, what do you think that major things and how greatly this can be complemented to kind of achieve or kind of tackle the bigger problems like sort of in origin or any other problems?
Oh, absolutely. It's essential that to fully exploit the various platforms we have, it's essential to make them work together. So for Parker Solar Probe in particular, Parker Solar Probe never leaves the punch field of view. We will always be imaging it,
Yes.
uh, or even though we don't resolve it. Uh, so during a perihelion pass, we can see for the first time a fully cross-scale picture of the solar wind in the outer corona. The scale contrast between the smallest things seen by Parker Solar Probe, which are on the order of hundreds of meters, and the largest things that we see with Punch, order of tens or 100 gigameters, that's almost a factor of a billion in linear scale. We've never seen a cross-scale study like that before. So we can capture both ends of the turbulent spectrum, all the way from the energy-bearing range at the very largest scales to the dissipative range at the very smallest scales. And we can capture that simultaneously by merging data from Punch and from Parker Solar Probe. So I'm very excited about that. So we can see, for example, uh, we'll find out about the origins of turbulence in the solar wind. The solar wind is gusty at the Earth. Why? Is that because of uh, turbulent eddies forming on the way out, or is it because primarily of individual ejecta leaving the sun? We know both of those things occur. What's the balance, right? Do they relate to one another? Are there multiple kinds of turbulence that are involved? Uh, there's a solar wind heating problem. The solar wind is something like 1,000 times hotter than you would expect from adiabatic expansion of the coronal material.
Yeah.
Where's that heat coming from? Is it being coupled all the way down from kinetic energy on the largest scales, all the way down to the dissipative scale where it shows up as heat? Um, is there reconnective heating going on en route? Is there some other process? These kinds of questions really aren't solvable without these very large sort of cross-scale comparisons. And I'm really looking forward to that.
Yes, yes, true, true. So apart from solar wind, do you think that Punch in coordination with PSP or the in situ spacecrafts can also kind of give much more information than earlier about CMEs, how the CMEs are evolving in the heliosphere, maybe their deformation or something like that?
Right now, we have an interesting situation with CMEs. We we see them on the sun. We know a great deal about the magnetic systems that form them and how they are released. But then once they leave the coronagraphic field of view, there's almost nothing until they impact a probe near the Earth.
Yes.
This is reflected both in the amount of argument over whether, for example, CME deflection is a thing or not, uh, or over the degree to which CMEs evolve as they propagate. This is when you see argument, that's reflective of not enough data, right? People have ideas and develop them, and we discuss those at meetings and publish disagreeing papers. And in some ways, that's the exciting part of science. But resolving those questions in those cases generally requires more information. Uh, so Punch will be the first mission to be able to routinely track CMEs, especially at high resolution, from the sun outward across the solar system. We'll be measuring their structure in 3D, so we can determine things like uh, how much interaction occurs between the CME and the pileup in the front. Do shocks form, and what structure do they have? Is linear shock theory sufficient, or do the leading edges of shocks form crinkled or even fractal surfaces that might interfere differently or give rise differently to solar energetic particles? So yes, we will be tracking CMEs from sun to earth routinely for the first time.
Yes, yes. True. So interesting time for sure for the solar wind, CME, solar heliosphere community. So for someone who does simulations, like person like me, or someone who is doing machine learning, so what they can do in this regard to kind of address these kind of problems and assist into the observations of these spacecrafts.
So simulations by themselves, as you know, tell you about your simulation code. Um, what's really important is being able to constrain them. And
Yes.
so Punch will resolve the large scale structures of a CME, but can't directly discern the microphysics. Uh, the very best type of outcome is we'll be able to constrain models that are simulated at the micro level. Uh, and so combining and comparing simulation data and Punch tracking data uh, ought to bear a great deal of fruit in terms of understanding these important fluid phenomena in our inner solar system.
Yeah,
Uh,
true, true.
Machine learning, I'm skeptical of, because in many ways, a machine learning system is specifically designed to generate plausible output. And we as scientists look for plausible things. And so it's very, very easy to fool ourselves, right?
Yes.
By looking at this output that's been specifically engineered to be plausible. Uh, so that's not to say it's useless. It's just to say we need to be very careful about the results we derive from it. But I think there is a role for AI to play, finding particular patterns for follow-up later on, or extracting information routinely that we already know how to find, right? That is to say, to find the accidentals of a particular event within the envelope of events that we've already observed. Finding and flagging anomalies for follow-up, I think, is something AI can do very well. So there's a great deal of benefit we should be able to get from AI.
Yeah.
On the other hand, we need to proceed carefully.
Yeah, true. Yeah. So the robust validation testing is for sure non-negotiable in the science terms. So coming to this part that we have different pieces and the punch is the new big person in the game. So how do you think in a long term in the roadmap of heliophysics as well as space weather prediction about this whole current situation?
So, in terms of those are two separate things, right? There's forecasting, which is an operational activity that we do based on knowledge we already have. And there's research, which is, if you will, fundamental science. Even if it's applied science, it's still fundamental science, learning about the universe around us. So in terms of the map for the next couple of decades, I see heliophysics very much on a course of unification. These various fields have become very sophisticated and separate. Solar physics, solar wind physics, geospace physics, planetary magnetospheric physics. Um, these have evolved in the early days into separate specialties. And there's a great deal of work to be done merging those specialties to a coherent whole. So that's where I see the largest and most interesting results coming. In terms of forecasting, of course, we expect that tracking CMEs will greatly improve forecasting, and we're very much looking forward to that. Uh, I like to compare Punch to the weather satellites that we have in geosynchronous orbit, right? You can imagine trying to track a hurricane without having access to imaging from geo.
Yeah.
Uh, it's very different, right? And in fact, it was very different in the days before. So for forecasting, that's an operation where we're trying to identify the accidentals of a particular event, right? Will this particular event impact us? And that's very difficult with current technology. So with Punch, we're hoping that we'll be able to revolutionize space weather forecasting. Right now, we get observations of each event near the sun, and then we have to extrapolate with models out across the void. Uh, as you know, it's not really a void, it's full of
Yeah.
other phenomena. And
Yeah.
so the accuracy of the simulations is very limited by sparse data. Uh, so by being able to track individual events, we ought to be able to see the same kinds of gains we saw when we started tracking hurricanes with geosynchronous satellites. You can imagine trying to track a hurricane if all you have is a few weather stations,
Yeah.
uh, as compared to looking down with a camera from orbit and seeing the storm evolve and move.
Mhm. Yes. True, true, true. Yeah, so definitely Punch, the way I'm seeing it, holds great value in space weather prediction as well. Uh, and we know that space weather is not only about the CME, the stream interaction regions, co-rotating regions, which are basically the background solar wind, which the Punch will be mainly focusing on very much in a greater detail. So do you think that with the increasing awareness of the space weather impacts, do you see some models coming from Punch team providing some kind of alert about these space weather events?
So Punch itself is not an operational mission. We are a research mission, but we are providing quasi real-time data to NOAA. There's a program called Quick Punch that NOAA has funded us to develop, and I believe will probably fund us to continue, where we'll produce slightly less photometric but rapid turnaround data after each ground pass so that forecasters can make use of the, if you will, the live stream from Punch. They care a lot about latency. Scientists don't
Mm,
care because,
mhm.
you know, you don't need to know before the event gets here.
Yeah.
Uh, Punch images only arrive when there's a ground pass, and that's once a day for most of the spacecraft. The narrow field imager has 6 passes per day, and so 4-hour latency, which is short enough that it's actually of use to NOAA forecasters. So we're pretty happy to provide that.
All till now, we have been talking about solar and heliospheric physics and how the Punch, the new big elephant in the room, is kind of getting us the new problems to be solved. But how about different fields which are not from the solar and heliophysics? Is Punch going to give us something about those as well?
Absolutely. I like to say that, one person's noise is another person's signal. Uh, and with Punch, we had to remove the backgrounds. The real innovation here is developing a routine way to remove a background that's 1,000 times brighter than what we're looking for.
Mm.
But what
Okay.
we found in the course of developing those tools is that the backgrounds themselves are very interesting. We will produce the world's most efficient, or we will produce the world's most sensitive polarized star map ever made, because
Yeah.
we have to identify and remove the polarized light coming from the stars. It turns out the polarization of the star field is caused by the interstellar medium polarizing unpolarized starlight. And so we can learn something about the galactic magnetic field that way.
Wow.
Uh,
Okay.
we'll we'll be imaging almost every asteroid in the solar system as we orbit the sun, and of course, editing them out of our main data. Uh, and the brightest thing in our images is the F corona, the dust cloud that orbits the sun. So there's a great deal of work to be done in understanding interplanetary dust. I didn't know this until this meeting in Moudon, but
Mm.
there's a dust cycle in the solar system with asteroids impacting and grinding up and dust making its way into the center. Uh, and then dissipating and coming back out on hyperbolic orbits. It's fascinating. It's a very rich field, and it's not a large field in part because measurements are hard to get. Uh, but by routinely imaging the dust, we hope to be able to advance there. So it's sort of fun that although we're probing into a heliophysics problem, as a side effect, we'll get data that should help with these other fields too.
Okay. So looking ahead, so this mission from the concept to launch and now we have started getting the data. It's very exciting and energizing. So do you have some kind of suggestions or guidance to young scientists who are thinking to lead similar projects into the future?
Mhm. I do. Uh, as a young scientist, focus on the results. Figure out what you need and if see do everything you can to work around it. When somebody comes to me and asks to work with me as a graduate student, I always give them the advice, if you can imagine doing anything else with your life other than research, do that. Don't go to grad school, right? Drop out now because Um, a life in research is not for everybody, right?
Mm.
What we do is it can be construed as tedious and boring. It requires an incredible commitment. We get occasional rewards. The hard work is its own reward. And if you're broken in a certain way, like me, right, it's the best thing ever because
Mm.
you're probing the secrets of the universe, you're reaching out and doing amazing things. But not all humans like that. That's not rewarding to all humans. And so if you can imagine doing anything else, you probably should. And the same thing is true for missions, right? You want to find out everything you can with the information you have. And then only if you reach a brick wall do you look towards something as expensive and difficult and time consuming as a mission. Uh, Punch is something that well, we started it in 2015. That was 10 years ago. Uh, and it's been an interesting and exciting journey. But throughout that time, that's been what I've been doing, as opposed to getting out more papers or investigating some of the other questions that have been of strong interest. And so that's why I say it's a public service to lead a mission. The community needs this data. I personally want to see this data. I wanted to see it enough that I was willing to see it through. And that's a good reason, I think, to do a mission. And so as a young person, you tend to look and see the leaders of the field and think, I want to be like that. Well, those people are largely doing what they're doing reluctantly because they will achieve something as a result of it. right? Leading a mission isn't an end goal in itself, it's a means to a goal.
So to all the young folks who's listening, so it's very competitive, very hard, and like Craig said, if you can do something else, do that. Okay. So finally, on a personal note, so what continues to excite you to do this difficult job, so demanding job till today?
I am thrilled to be on the cutting edge of knowledge. I mean, what drives me and what should drive young researchers too is we work on all kinds of difficult problems. We try to get our code to work, we try to figure out new things to see. But every once in a great while, once in a while, maybe every year or two, if you're lucky, we get to see something nobody has ever seen before, ever, right? We can learn something about the universe that nobody has ever known, right? These things are there to be found. And that is the best reward ever, right? Recognizing that you're advancing human knowledge. We really are, in some ways, the brain trust of humanity, right? All of the world benefits from the knowledge we gain. And it's important to remember that. But it's also what drives me, right? I love doing this stuff. I love finding things out. I love figuring things out, solving puzzles. But at the end of the day, what makes me come to work, even when it's difficult, is knowing that what we're doing is something nobody has ever done before in whatever small way we're doing it.
Yeah, true. Yeah, definitely very inspiring for me as well. Maybe one fun question. So if you could go back and witness any one moment in the history of solar physics, and maybe an eclipse, a launch, or a discovery, what it would be and why?
Oh. I think I would go back to see Bernard Liot putting together his coronagraph
Mm,
because I had a chance recently to see that. I went to a meeting on dust in Moudon, Paris, or Moudon outside of Paris in France. Uh, and I saw the original coronagraph. And, we're used to thinking of instruments as very high-tech things and very precisely made things, expensive things. Um, the coronagraph that he used to image the corona and do real science with is cobbled together. It's like a piece of junk. It's like put together from old boards that he had lying around and some optics that he had on hand. And it's put together in a very clever way. Uh, but wow, what a neat thing, right? This reminder that yes, we're driven to do very precise things, and in the case of a space mission, we're driven to do very highly engineered and expensive things. But that's not important to the science. What's important to the science is doing something that hasn't been done before. And in the case of Leo's coronagraph, nobody had ever built one of those before. And so he put it together with what he had on hand, the materials around his lab, uh, and didn't let sort of a lack of precision stop him. And he was able to do something that hadn't been done and see things nobody had seen before. Uh, with what today we can look back at and say, oh my gosh, that it, I mean, it's made out of pieces of flooring, right? Were nailed together and very cleverly designed and engineered, but fundamentally uh, just exactly what's needed and no more.
true. Yeah. So the main thing is to solve the problem or find something new, not to make things complicated. If required, then we'll have to obviously, just you said, we needed four small spacecrafts for the punch. So it was really, really enlightening for us. So thank you, Craig, for joining us. And I hope the listeners will have a lot of things to learn from this podcast. So thanks again for joining the Indus Podcast. Thank you.
Thank you for having me. It's been wonderful talking with you, and good luck with the rest of these. I'm looking forward to them.
Yeah, and good luck and congratulations for the first flight, and as well as best wishes for a very, very successful punch mission.
Thank you.
Yeah, thank you.